a little interlude here to discuss forests. Similar to a tree, a forest is a graph with no cycles. The missing component here that would make this a tree is the connectedness that I'm not assuming. Over here we have an example of a forest on 6 vertices. Here it's a labeled forest. And we can see there are 2 connected components. 1, 2, 3, and 4 are connected, and 5 and 6 are connected. The graph has no cycles, so this is a forest. It's not a tree though, because it's not connected. Of course, a forest is just a union of trees. And one thing we want to do is we want to count edges in a forest. That's a nice way to get started and get familiar with it. This forest, we can see, has 6 vertices and 4 edges. But we can take another tree, or let's take another forest. So we'll take the same 6 vertices, and now let's add some edges. So this is a different way we could make a forest. And now when we look at the forest, okay, this forest now has 3 trees. So it's a different forest on the same vertex set, and it has a different number of edges. Remember, we knew that trees on n vertices always have n-1 edges. So how many edges do we get on a forest? So it doesn't just depend on the number of vertices. Proposition, given a forest with n vertices, we need more information. And let's say k trees. K is the number of connected components. Given a forest, say F, F has how many edges? Okay, let's think about it and let's look at this example. So here we have 6 vertices and 2 connected components and 4 edges. Okay, so what you want to try to do is relate the 6, the 2, and the 4. Now remember, in the case where we have 1 tree, so let's remind ourselves what that is. A tree, which is a forest with k equal 1, has n-1 edges. So we take the case that we know, and we take the case that we have here, these examples, and say, okay, how can we generalize this statement up here? How many edges do we get in a forest? And so we might want to guess n minus k. And then we'll check, of course, is this consistent with the examples we have here? Here we have 6 vertices, 2 components, and 6 minus 2, which is 4 edges. Here we have 6 vertices. We have 1, 2, 3 connected components, and we have 6 minus 3, which is 3 edges. So in fact, this is true, and you can prove it by induction. It's a great exercise that I highly recommend. But what I want to do is I'm going to use this fact that we're going to take for granted about the number of edges in a forest, and I want to prove a remarkable lemma about forests. That's a little bit surprising. So what's a lemma? A lemma is a statement that I'm going to use later to prove a theorem. So we're going to use this lemma in the next video to prove that Kruskal's algorithm actually does find us the minimum weight spanning tree. But before we get to that, let's prove the lemma. It's just a statement about forests. Given 2 forests, which I have here, on the same vertex set, which of course I do, the numbers 1 to 6, if the number of edges of forest 1, which apparently is down here, is less than the number of edges of forest 2, which is up here, then there's some edge up here that I could add down here, so the result is still a forest. Let's see that that's true, okay? It's saying that there's some edge up here that I can add to this forest so that the result down here is still a forest. This edge, can I do that? Well, no, because that edge is already there, and this would make it not a simple graph, and that would give us a cycle. So no, not that one. What about this edge? If I added this edge in here, what would I get? I would get a cycle right here, so I cannot add this edge. Okay, what about this edge? If I put this edge in here, aha, that's perfectly good. There's no reason I can't put this edge here, and now I've not created a cycle. That's what the statement of the lemma says, that there is some edge. Now in this case, I could also take this one and add it here. That also works to avoid creating a cycle. So it doesn't matter that I can do it more than once. It only matters that I can do it. We'll see why this lemma is so useful, but before we do that, let's prove it. So how do we prove such a statement? Given 2 forests, there's some edge I can add. So finding that edge might be difficult, okay? So in a case like this, when I'm not sure how to find the edge, because it really depends on what my graph is, one of the best ways to do it is go for a proof by contradiction. So we're going to suppose not. Suppose not. So that means that every edge E in forest 2, so that's an E of F2, the edge set of forest 2 creates a cycle in forest 1. What does that mean? Well, let's think about some consequences of that, okay? So if every edge that I add here, right, creates a cycle, then I have to be adding an edge within the same tree, okay? If I have two different trees and I add an edge, there's no problem. I can't create a cycle when I connect two trees, right? Because there's no cycle between either tree. So adding an edge to connect two trees won't be a problem. So what does this mean? So this tells me, therefore, it creates a cycle in F1. Sorry, this implies that every edge, every E, must connect vertices of the same tree in F1. So what does that mean? What's the implication of that statement? So that's going to tell me something really important. That's going to tell me something about the number of trees. So it tells me that, let's say K2 is the number of trees in, so this is the number of trees in F2. What does that have to be? That has to be at least as big as K1, which is the number of trees in F1. So it tells me that K2 has to have at least as many trees as F1. Otherwise, I wouldn't have this statement that I'm always connecting within the same tree. Okay, well, let's cover up our trees for a second and continue with the proof. Okay, so I've now concluded that. But, we're almost done, but remember that we have a bunch of assumptions here that we've made in our statement. So one of them is right here. So the number of edges, this is the statement that I'm going to use, of F1 is less than the number of edges of F2. Remember the lemma we just proved? The number of edges is the number of vertices minus the number of trees. That's the number of this is the number of edges in F1. And that is strictly less than the number of edges in F2, which is n minus K2. It's the same n because they're both forests on the same vertex set. So if I just think about this, I can subtract n from both sides. So I'm going to get minus K1 is less than minus K2. And now I can multiply by -1, which flips my sign. That tells me that K1 is strictly bigger than K2. So now look at what we have on the board. We know that K2 is greater than or equal to K1. So, but we just proved that K2 is greater than or equal to K1. These two statements cannot be reconciled. This is our contradiction. That's the end of the proof. That's how we prove it. So we suppose not, and we arrive at a contradiction. Our contradiction comes from using the assumptions we had on edges to get one relationship between K1 and K2, the number of trees, and then we use the fact that there's some edge. So the conclusion that we want, when we say it's false, we get the other inequality. So this is a lemma that we'll keep in mind, and we'll see how it's useful in analyzing the greedy algorithm for finding minimum weight spanning trees.